Hey everyone, we are jumping straight into an absolutely incredible engineering detective story today. When we look at a modern, high-speed electric train, we just see the sleek, green solution to the climate crisis. But what we don't see is the completely hidden, highly volatile electrical battle happening in the cables just inches above that train. So in this explainer, we're going to reveal the invisible systems that power our world, the severe physical limits of our power grids, and the ingenious software algorithms racing to stop those grids from just entirely collapsing.
Okay, let's take a super quick look at our roadmap for today. We're going to cover the green rail paradox, reaching the hardware limit, the mixed traffic problem, the software solution, and finally, the perfect algorithmic run.
All right, let's kick things off with Section 1, the green rail paradox. So, all over the world, international climate policies are applying this really intense pressure to clean up transport, right? And we have to do it without reducing actual travel demand. Take the UK, for example. They have a strict legislative milestone to completely phase out diesel rail traction by the year 2040. It's a really hard deadline, and it basically assumes we can just plug everything into the grid to hit these net zero targets. Which brings us to the most critical question of this entire explainer. Can our current power grid actually handle that kind of load? See, there is a massive deficit in what engineers call power headroom. For decades, we just relied on high energy density diesel, which, brings its own fuel right along with it. If we ban diesel and swap it for direct electric power, we're suddenly shifting thousands of tons of dynamic moving weight, literally entire steel behemoths, directly onto the national grid. And if we aren't incredibly careful, we risk breaking the grid's physical limits entirely. That leads us right into Section 2, reaching the hardware limit. Now, we can't just buy our way out of this by laying down infinite copper wire across all our rural networks. That's just way too expensive. Instead, modern networks use some really specific infrastructure. Traditionally, we relied on transformer architectures, which draw severely unbalanced loads from the national grid and require these really annoying neutral sections on the tracks where trains actually lose power for a second. But the modern fix? Those are static frequency converters, or SFCs. They use advanced power electronics to balance the grid perfectly. But there's a catch. They have a fatal flaw: hard, absolute current limits. If a train asks for way too much power all at once, the SFC can't just push through it. It actively cuts the power off to protect itself. Which brings us to our third stop, the mixed traffic problem. So the real world obviously doesn't operate in a vacuum, and severe bottlenecks happen precisely because we're mixing wildly different types of trains on the exact same network. Think about it. On one hand, you have passenger trains. They're lightweight, they're fast. They need a highly transient, sharp spike in power to quickly accelerate, and then their demand just drops right off. But on the other hand, you have heavy freight trains, fully laden locomotives dragging over 2,000 tons of cargo. They have massive inertia, which means they demand a sluggish, continuous, and massive current draw just to get moving and fight track gradients. And when you map out their electrical demand profiles, the clash is completely obvious. You've got the sharp, quick power spike of a passenger unit running right up against a massive, sustained dome of electrical demand from the heavy freight locomotive. That continuous current acts like a giant power sink on the local network. It literally depresses the voltage in the overhead cables for miles around it. And that brings us to a frankly terrifying number for railway engineers: 19 kilovolts. The standard overhead line runs at 25 kilovolts. You can kind of think of the grid like a shared neighborhood water pipe. When one massive freight train opens its valve to the absolute maximum, it drops the water pressure for everyone else on the street. If the voltage sags below this critical 19 kilovolt cutoff threshold, modern trains will automatically enforce a power limit just to protect their own circuitry. So, as a heavy freight train accelerates, it can physically drag the voltage down so incredibly hard that it drops straight through that threshold. And when that happens, trailing trains are starved of power, and the system can even trip its circuit breakers to protect itself. And I probably don't have to tell you, but when circuit breakers trip, trains get stranded, timetables totally collapse, and massive financial penalties are slapped on the operators. Okay, so how do we fix it? Section 4, enter the software solution. Since we can't just easily change the physical hardware everywhere, we have to rely on digital heroes to change the behavior of the trains themselves, using algorithmic energy management strategies. But before we get into the shiny new software, it helps to understand why the old software failed. Early simulation models were what engineers call grid blind. They calculated the mathematically perfect, absolute most energy-efficient way to drive one single train. But they assumed that train was connected to an infinite power source. So a grid-blind algorithm might tell a passenger train to accelerate at maximum power at the exact same second a freight train miles away is already dragging the grid voltage down. In the messy real world, this mathematically optimal profile was actually a huge hazard. To fix this, researchers developed multi-train train track power or TTP simulations. Think of this software as an air traffic controller, but for electricity. Instead of just looking at one train, it simulates multiple trains simultaneously. It intentionally staggers the acceleration of heavy freight so they don't overlap and blow the system. It flattens the peak power demand to respect those hardware limits we talked about. And this is the really cool part. It synchronizes regenerative braking, meaning the algorithm can time things so perfectly that when a passenger train hits the brakes, which generates completely free electrical kinetic energy, a freight train a few miles away uses that exact burst of energy to accelerate. It keeps the load off the national grid entirely.
All right, on to our final section, the perfect algorithmic run. So the ultimate goal of all these advanced algorithms is to look at a sprawling, chaotic railway network and find the mathematically exact global minimum for energy use across the entire fleet. When we strip away all the chaos, the analytical models tell us that the theoretical optimal eco-driving sequence for any train follows 4 really strict phases. First, maximum power to accelerate efficiently. Second, speed hold for cruising. Third, coasting, where you just use momentum with 0 power draw. And finally, maximum braking. The challenge, of course, is safely choreographing this exact 4-step dance for dozens of trains at once without ever letting their combined power draw drop the grid below that 19 kilovolt limit. But here is where we hit the absolute bleeding edge of current research, the computational bottleneck. Simulating the exact physics, the precise location, and the electrical coupling of dozens of trains over a moving topography, it creates an exponential state space. It is incredibly, mind-bendingly heavy math. So multi-train algorithms are constantly forced into this trade-off. Do they spend hours calculating the absolute, mathematically guaranteed perfect schedule? A schedule which, by the way, becomes completely useless if one single commuter train is delayed by 5 minutes because someone held the doors open? Or do they use clever approximations to stay computationally viable and function in real time? And that leaves us with a truly fascinating gap between mathematical perfection and human reality. We now have algorithms that can map out an absolute masterclass in grid-aware, energy-saving train trajectories. But can unpredictable human drivers who are dealing with weather, delays, and fatigue actually execute these microscopic speed adjustments? Or does this all suggest that to truly protect our fragile grid and actually hit our net zero targets, full automated train operation is our